Sure. Okay, so is my presentation visible?
Yes, Ijaz, your screen is visible.
Okay, so yeah, so thank you, Edna, for the introduction. And let's get started. So what we are going to talk about today in an hour or so is we'll talk about little bit of everything. Meaning I'm not the presentation is designed in a way not to completely focus on the theory part or the application parts. We will touch on all aspects little bit. Such a way that at the end of the session, all of you should have a basic understanding of how mass spectrometry is actually useful. And for this case, it is in for pharma applications, but it can be applied to any other field as well. Okay, so let's get started. I mean, yeah. So this is the agenda for the today's session. We'll start with introduction. And one thing that I would like to mention here is basically when an analytical scientist talks about mass spec, he or she is invariably referring to an LCMS setup, meaning an LC is connected to the mass spec. So that's by default. If I today also if I'm referring to a mass spec, it means that I have an LC that is connected to the mass spec. So we'll start with the LC part. We'll look at the principle of HPLC, and in HPLC comes in various flavors. You have a lot of variety in HPLC. So today we are going to focus on one of the most primarily used HPLC technique coupled to mass spec. It is reverse phase HPLC. We are going to look at the HPLC setup, how it looks like, what are the modules involved in the HPLC setup, and similar thing we are going to look at the mass spec. We are going to study about the principle of mass spectrometry. We are going to look at the setup of mass spectrometer. Then we are going to talk about briefly about various modules in the mass spec, and then I'm going to talk about little bit about the protein workflow. So this will be the application part where I would I'll show you some data that we generally generate in in our laboratory, and I'll walk you through the basics of data. So this is the agenda laid out today. And what is the learning at the end? If everything goes well, at the end of the session, you will understand how a complex molecule like this. So this is a typical molecule that we get in our laboratory for analysis. It's a monoclonal antibody. It's a very big molecule, as you can see from the molecular formula as well as weight. It is is a sufficiently big molecule. So we would understand how mass spec as such can be helpful in reducing the structure or rather confirming the structure of such a large molecule. So at the end of the session, you'll have a general understanding of utility of the mass spec with respect to a slightly complicated molecule. So generally, in some presentation, you might have seen that people talk about small molecules when they try to explain the principle of mass spec or a basic data analysis. So here I've purposely taken a slightly complicated molecule, so I get to tell you guys more about the higher part or the high end mass spec that we use. What is the need? What is the need to use a high resolution mass spec? Or what is the need to use a mass spec that has a very high scanning speed? So that is the purpose of taking a slightly complicated molecule. But no worries, even if we have no understanding of proteins or antibodies or any large biomolecules, no worries. We are going to start from the basics and we are going to cover most of the aspects. So no preliminary knowledge of biology or proteins or microbiology or biotech is required. Okay. So let's start. Let's get started. So as I said, when I talk about mass spec, I'm invariably referring to a LCMS setup, meaning an LC part is connected to the mass spec. That being said, can an LC operate independently or a mass spec operate independently? Yes, definitely yes. Can operate independently, and we do operate it independently when there are certain requirements. But it comes with various advantages that you'll appreciate once we go dig deeper into the presentation. You'll understand why is it important to connect an HPLC to a mass spec, and what kind of data we generate using an HPLC MS setup. Okay. So most of you, if you have some exposure to a typical analysis lab, then HPLC is one of the most important equipment that we use, at least in the pharma domain. So we know the principle. We are going to talk about the principle as well. But if you talk about HPLC, what it does, it separates the component. So when we are working in an industry or 90 to 99% of the time, we'll work with a complex molecule. The complex mixture is a mixture containing number of chemical components together. So it's very intuitive. We cannot inject all the components together. We'll get a very complicated spectra or a complicated chromatogram, which will be not be able to identify what peak belongs to. So in that case, what we do is we pass this complex mixture to an LC system. The LC system will separate the components. We'll talk about how it separates, and the separated components are then injected into the mass spec. So what we literally do is we literally can connect the output of the HPLC to the input of the MS, and that's how the flow is connected, and that's how we get some mass spectrum. So these are the typical. These are not the only, but are typical mass spectrometers that are currently available in the market. As Edna pointed out, we have NCBA, that's the Center for Biopharma Analysis. We have the Orbitrap model with us, and in the CAMPS facility, we have a QTOF model with us. We'll talk about what is QTOF, what is Orbitrap, what are the principles of that. Actually, that will also be talked about. But these are some of the vendors and some of the typical setups that are currently in the market. The middle one you see is the triple quadruple by Shimadzu. There are other vendors also, but just for the sake of giving you a brief idea of how the equipment looks like and what is the setup, I have included these things. Okay, so let's talk about the schematics. When you talk about LCMS, so what are the various modules or what are the various components of an LCMS setup? So when we start developing the methods, these are the components that we need to play with. And so we'll talk about this in detail in the coming slides, but let us talk about the HPLC component. So when I talk about an HPLC component, it has various components. It can we can add, delete, or modify any component, but these are the basic components. So we have a solvent cabinet, then we have a degasser, then we have a pump, the auto sampler, and the column compartment. When we talk about MS components, the various modules that are attached to a MS component is the ionization source, the mass analyzer, and the detector. Now, why the software? Why the data acquisition? Because when you talk about an LCMS setup, and we are talking about complex molecules or complex sample mixture, it will generate a complicated spectra. So manual interpretation or manual, analysis or even the acquisition becomes difficult because let's say a typical data file that we generate for let's say a typical mass peptide mapping, it is somewhere around 500 to 600 MB. And we do proteomics. When we do proteomics complex protein analysis, the raw data file size goes up to GB level also. So manual interpretation becomes a problem. So that also that is being taken care of by the software. So we have a software for acquisition where you control the instrument through the software. Then we have software for analysis also, where a lot of softwares are chemometric softwares are available. Free to use, paid versions, a lot of things are available, and the softwares for reporting as well. Because you need when you talk about submissions and something like that, you need a very very defined set of rules for reporting. What kind of peaks that you should put, what is a good peak, what is a bad peak, what is a good spectra, what is a bad spectra. So we need softwares for reporting as well. So we are going to look at that as well. So as I said, the starting point of an LCMS experiment is the HPLC. You need to choose the right HPLC. Now, most of us are aware of what HPLC does, but this I put it in a single slide so for continuity purposes. So what does HPLC does? HPLC stands for high performance liquid chromatography. It is used to separate and identify different components in a sample. In our case, it is a protein or a peptide that we are talking. So when we have a complex mixture, as I said, we should not rather directly inject it into the mass spec, but because every component might give a signal, and all signals will, jump up, and the interpretation of that spectra becomes complicated. So what we do, we try to separate it on an HPLC component, HPLC system, and then we inject it into the mass spec. So, as many of us know, HPLC has various flavors. HPLC has various types. What kind of HPLC that you should use is a good. A lot of people ask, what kind of HPLC should you use? For example, here I mentioned size exclusion is one kind of high pressure HPLC that we can do, or ion exchange is what kind of HPLC what you can do. So the type of HPLC that you should use depends upon the physicochemical properties of the compound or the mixture of interest. For example, let's talk about if you have a complex mixture, if you have a mixture of samples where you have molecules or where you have chemical entities that have different sizes. So you see, if you see here, let's talk about size exclusion. So I have a big molecule, the blue color one, and a smaller molecule that is red color one. Now I have this complex mixture, and I want to separate it. So how would I use, which HPLC I'll use? I'll use the size exclusion, because size exclusion will be able to take advantage of this difference in the size. The physicochemical properties, the difference in the size, and size exclusion will be able to separate this complex mixture based on size. Okay, so just a passing comment. So if the size is longer, higher, if the size is bigger, if the protein is very big in size, it will elute earlier because it will not go into the pores, and if the size is smaller, it will go into the pore and it will come late. So you can see the big blue color molecules come first in the RT. They have a smaller RT, and the red smaller color molecules will elute later. So, and one more example would be an ion exchange. If your molecule is highly charged, or there is difference in the charge density, or some molecules are positively charged or negatively charged, you can take an advantage of ion exchange. So, does that mean that any chromatography can be coupled with a mass spec? Theoretically, yes, but size exclusion, you should always use, but there is a compatibility issue, meaning size exclusion if you are using certain mobile phases, the mobile phase is used to separate, but the mobile phase that you are using should be compatible with the LCMS part. Or very briefly, if I want to mention, you are discouraged to use any mobile phase that are non-volatile. So you should use mobile phases that are volatile. The reason we'll look in the next couple of slides. So yes, you can compare, you can couple a size exclusion to a mass spec, provided that your mobile phase is compatible with mass spec. One of the criteria of checking for the compatibility is that it should be what do you say, volatile. We'll look at it. So you need to choose a proper HPLC. In our case, 90% of the time we are using LCMS part. LCMS we are using RPLC, reverse phase chromatography. Look at in the next slide. But certain sizes, certain time we are using ion exchange. Certain time we are using SEC also. That is size exclusion chromatography. Also we are using. So that depends upon what your requirement is. Okay, now this is the chromatography that we are currently using. For 90% of our application, we are using reverse phase chromatography. So in reverse phase chromatography, what is the physicochemical property that we are going to take advantage of? It is the hydrophobicity. Many of us know that we are using hydrophobicity. Hydrophobicity is the core principle of operation for a reverse phase chromatography. So let us talk about this image. So let's say I have three molecules, a triangle, just for the sake of understanding, a triangle, a square molecule, and a triangle, a circle, and a square molecule. Now let's say this molecule has high interaction with the stationary phase. This molecule has moderate interaction, and that meaning this molecule is highly retained by the stationary phase. This molecule is slightly retained, the yellow one, and the green one is very slightly retained, and the yellow one is moderately retained. So what happens when we start the mobile phase flow continuously through it, with the molecule that has very least interaction, in this case the green color square, it will elute earlier, followed by the moderate interaction, and then followed by the highest interaction molecule, the molecule that the stationary phase is catching to a very high degree. It is not letting it go. So we need to push the molecule by increasing the strength of the mobile phase, by using a lot of additives. That goes into the method development part. We are not going to talk about it today. But yeah, so sorry. So this is how this is how RPLC, reverse phase chromatography works. It works on the principle of hydrophobicity of the molecules of interest. Now let us talk about the setup. How does the actual setup looks like? So most of us might have seen the RPLC or chromatography setup. But let us talk about in the great detail. So one of the first component of an HPLC is the degasser. Now, this being said, what does the degasser do? Yeah, we are going to use a mobile phase. We are going to use mobile phases. We are going to use water as one of the main component of mobile phase. So water might have dissolved gases into it. And because we are going to use a high pressure system, the dissolved gases might impact the pumping system, because we are going to use pump to inject the mobile phase. It is like a heart. Right? What the heart is to the body, the HPLC pump is to the chromatography. Its main core function is to pump the mobile phase throughout the system. So if we have dissolved gases, it might create a pressure. It might create some problem with the pumping part. So that is why degasser is used. This being said, can you use a system without degassing? Yes, you can. You can use the system, but it's a good practice to incorporate a degasser into your HPLC setup. So If you are degasser, if you are not using degasser, if your degasser has problems, then what you might face is you might get erratic pressure variations because obviously the dissolved gases is not letting the pump to function normally because again inconsistency in flow delivery, yeah, you can directly correlate it and variation in the baseline because your flow rate and your pressure variation is there, your baseline might not be. So what you do? Let's say you don't have a degasser at all. So what you do? The minimum that you can do is sonicate your mobile phase. Sonicate your mobile phase to at least 10 to 15 minutes. Make sure that your whatever salts that you are dissolving in it is completely dissolved and filter it with a 0.45 micron filter membrane so that you make sure the effect of gases, dissolved gases is minimized. So that is a function of the degasser. Let's talk about the pump. The pump, as I said, is the heart of the HPLC system. Now, when you hear chromatographers or analytical scientists, they always talk in terms of pumps. So let's say I will not say when I'm talking to my colleagues or something like that. If they ask me what is your HPLC, I'll say it is a 400 bar system. So I'm annotating the HPLC with respect to my pump capacity. So when you talk about HPLC, the general cap is at a 400 bar system. If you have a ultra high performance, you have a UHPLC, then the UHPLC that we have it has a pump pressure of 1500. And then again, we have a nano LC as well. So nano LC is still higher, 2000 or something like that is there. So pump is the heart of the system. And most of the time, when we talk about HPLC, we judge the performance or judge the type of the equipment based on what is the capacity of the pump. 400 bar is a normal HPLC. 600, 800, 900, 1500 bar is a UHPLC, and we have nano LC that are still more powerful than that. So it is absolutely essential that your pumping is very good. Your pump is performing very well. If your pump is not performing very well, how would you know if your pressure is unstable? Like let's say you have kept the system for you have started the system and after an hour or so the pressure is not stabilizing. That means that the pressure is unstable. Then you need to look at the pump. What is there any problem with the pump? The other problem might be very high pressure. You're doing some experiments, let's say for a month or two, and you know that for this experiment you get a pressure of, let's say for this experiment and this column you get a pressure of 400 bar. Now suddenly you are getting 600 bar. So that should raise some signals. Why is the pressure very high? Most probably it is due to clogging. There is some clog in your tubing or some clogging in the pump that is increasing the pressure. So this is one thing that you should look into. The other thing might be very low pressure. Now very low pressure, that means very low pressure means again you're working with a certain set of experiments, and you generally know that you are getting 400 bar. Now today you are getting suddenly 100 bar or 200 bar or 50 bar. So that means very low pressure. The most obvious cause for low pressure is leak. If there is some leak in the system, your pressure will not be up to the mark. So you should start with leak. There are other factors as well, but you should start looking. The first thing that you should look when the pressure is very low, leaks. If there are any leaks in the system, resolve that leaks. Then you should be able to. You're good to go. Now, what is the trouble seeking? As I said, if there is a very high back pressure, check for blockages. If there is very low pressure, check for leakages. If there is inconsistency in the pressure, if there is unstable pressure, air bubbles. There might be air bubbles in your tubing, or the degassing might have not happened properly. That's why you are getting air bubbles. So these are certain cases or certain things that you should look when you are choosing a HPLC. What type of HPLC you actually want? Do you always want to go with UHPLC? No. If the requirement is not there, do an HPLC. If the requirement is still there, do UHPLC. If the requirement is very high, then choose an NLC. But there are pros and cons of using a high pressure system versus a low pressure system that we can talk someday. Okay. Now let's talk about auto sampler. So obviously we are not going to inject, if you have like let's say 50 vials, we are not going to sit on the equipment and inject manually 50 vials by our hands. We can do some other things that time. So we use an auto sampler. The function of the auto sampler is very simple. Pick up the sample and inject it into the system. Okay. Now what are the problems? Carryover. Carryover is an important problem. Let's say you are injecting three samples together, sample A, sample B, and sample C. Those three samples are totally different. But the signal you got in sample A, you are still getting the signal in the sample B also. That means carryover. Some part of sample A got stuck to your tubing or injector assembly, and that is being shown in sample B as well. So carryover is an important thing that you should look into. Incorrect vial position. Yeah, it is very trivial to mention, but when we are working in a high requirement environment, It happens. You were supposed to keep in your vials in PA1 and you somehow kept it in PA2. That happens with me quite a lot. So it is also important. You should keep it in a very in correct vial position. And it so happens that you forgot to check. You guys, we, at least I forget to check. And when the data is acquired, I say why I'm getting the totally different data. I go back to the sample vial and I said I injected the wrong vial. So this is a small part, but when you're working under pressure or you're working in a high performance company, this happens. And incomplete aspiration is also one thing. But nowadays, the engineering and the folks have taken have designed the system so well that this does not occur generally. But it is important. We are talking about quantitative analysis where you want to inject 2 microliter means 2 microliter should go into the system. If even 1.5 goes, you're going to get quantitatively different results. So incomplete aspiration is again a problem. So then you should ensure that if you want to inject 2 microliter, make sure that 2 microliter is actually getting injected into the system. There is no blockage or there is no air bubble that is interfering with this injection. Okay. So carryover, if you want to resolve carryover, ensure proper cleaning after each time, after you inject each vial into the system, make sure that you keep a cleaning vial also. And you say to the system, after you inject every sample, you get yourself clean with this cleaning vial. So that can be done. That is pretty routine. And yeah, again, incorrect vial position. Make sure that the sample trays kept in the right position. Your vials are kept in the right position. And incomplete expiration might also happen when when your cap, HPLC vial cap is too tightly fitted, so that air displacement. It works on the principle of air displacement. Make sure that you don't. This is again a practical thing that you guys that we realize when we start working actually. So make sure that your HPLC is while is not very tightly fitted, or it has a one slit in between. So the kind of slit that you choose or kind of cap that you choose also is also very important. You should choose a slitted cap or other cap that should not affect. So we can talk about it someday. So the other part is, or I forgot to mention one important part. So auto sampler. So auto sampler is simply you can use it as an auto sampler as well, but in certain cases you can make use of the auto sampler in to your advantage as well. So simply put, what it is doing, it is picking up the sample and it is injecting into the system. We can use this as a small automated reaction platform as well. For example, what you can do, you can put while A in position 1, while 2 in position 2. You can give a command to the system that take 1 ml of sample from the while A, take 1 ml of sample from the while B, put it in sample C, mix it, and then inject it. Okay, so this is a very unique application, and this again working in a high performance laboratory, this might be very useful to you because if you want to do some reaction, why don't you ask the HPLC to do it? Mix A and B, let it stay for about 15 minutes, and after that you inject the C into it, and then we can get to it. One slight application that I understand that we generally do is amino acids. So in amino acids, the vendors provide a specific kit, and everything is automated. You don't need to do any sample preparation, at least for the labeling part, manually. You can just give a set of commands to the auto sampler, mix this, keep it stable for let the reaction proceed for 15 minutes, and then inject it into the system. So, I mean, this is an intelligent use of LCMS that you get, or the vial that you can, or the auto sampler that you can do. Now, talking about the thermostat. So the basic function of the thermostat is to use the HPLC column. Okay, it used, but why there is a complete different module for thermostat? Because thermostat it regulates the temperature, and the temperature of the column is one of the very important aspect that you can modulate or that you can tweak while method development. The primary function of the thermostat is to regulate the temperature of the column. Okay, so what are the problems? Problems is leak. Most probably, if your column is clogged, you will see a leak in the thermostat. If your column is not properly equilibrated, or if there is a lot of back pressure, your peak profile shape is not good. So first thing you should do when your leak is there, check for the column. If you are using a column that has not been used for a couple of months, so what you should do is you should first allow the column to get wetted. Very bluntly put, you should allow the column stationary phase to regenerate, and after regenerating, you should use the column. So check for leaks, check for temperature maintenance. Now again, the simple function of the column compartment is to store a column. But now we have a column compartment that can house 4 columns or 5 columns together. And when you talk about DOE, design of experiments, or intelligence way to develop your method. So when you're talking about method development, what you do is you come on day one, you start working with column A, and then you identify at the end of the day that's not going to work. Column A is not going to work, so you plan that tomorrow I'll come and start with column B. Now this process can also be automated. What you can do, we have a column compartment that can house 4 columns together. So before leaving, what you can do, you can connect all the 4 columns to the column via the column compartment, and you can again give a command. Run the 10 samples using column A, run 10 samples using column B, and so on. And by the time, and you will leave it for overnight. So by the time you come tomorrow, what normally would require you 1 week, we have done it in overnight, ideally, because yeah, there are other cases also, the other things also we should take into. But this is the capacity of modern systems. Instead of one single column, you can keep 4 columns together. You can give a command, and by the time you come tomorrow, you have data where you have analyzed the same sample on 4 different columns, and then you can use that information to do very quick method development. So that comes into picture when you started design of experiment, that kind of stuff. You will get to know more about that. Use of column compartment. The other part I'm not talking about, this is the detector. Now detector can be anything. As I said, my column inlet is this, my column output is this. So I can connect this column output directly to an LCMS part that we'll talk. Or what I can do, I can connect the column output to my UV detector, and the UV detector and then the UV detector output can go into the mass spec. So I will get a UV data as well, or I will get a mass spec data as well. You can bring as many detectors you want. For example, there is a certain case where we use UV, FLR, and mass spec together. So we have something called our outlet of the column compartment will go into the inlet of UV. Outlet of the UV will go into a inlet of the fluorescence detector, and outlet of the fluorescence detector will go into the inlet of the mass spec. Now people will ask me where the people ask you generally, where the outlet of the mass spec goes. It goes into the bin, because mass spec we know is a destructive technique. It will while detecting the molecule, it will destroy the molecule. So we cannot take the eluate out of the mass spec. UV is not a destructive technique. What it does, it records the measurement. It records the UV absorbance. That's it. So it is not a destructive. So the take home message here is you can connect n number of non-destructive uh, detectors before the mass spec. But after the mass spec, you cannot connect anything, because mass spec itself is a destructive technique. The process involves destruction of the molecule while analyzing the molecule. So that is an important point to remember. Now we have taken a look at the mass units of HPLC. Now let's talk about mass spec. So mass spec again is a modulated system. Modulated means you cannot disconnect anything, but it has various components. So the first thing I said here, here is my HPLC and the inlet of the HPLC. Here, this is the inlet of the HPLC. It will go into the mass spec, and from here the mass spec picks on and does the analysis. So mass spec also has a lot of mass spec also has a lot of data, a lot of components attached to it, and it's quite complicated. So you'll appreciate it when we start doing it, looking at the data analysis. Analysis of mass spec data is not as simple as compared to HPLC or other equipment, because it generates complicated data. So yes, mass spec, the various components of mass spec is the source, the analyzer, and the detector, and the data system is obviously other. In this, the main game happens in the source and analyzer. So these are again the heart of the mass spec. Source is also pretty common, but analyzer is the heart of the equipment. Again, when critical scientists they talk with each other, they always refer to the mass spec with respect to package. So what kind of mass spec that you have? Like I might say that I have a Q-top mass spec. Somebody might say that I have an Orbitrap mass spec. So that means the analyzer in that is either an Orbitrap or a Q-top or a triple quad. So that is the schematic of how mass spec looks like. What are the components? Now let's talk about the principle. It's very important. The principle is, mass spec is not a universal technique. Only those molecules that can be ionized. Ionized means only those molecules that can sustain a charge over it can be detected by mass spec. So per se, it is not a universal technique, but can it be made universal? To a certain extent, yes, you can use some modification. You can do some changes in your sample preparation by so that the molecule can sustain a charge over it, and then it is detected. But that you should remember, it is not the only those compounds that can sustain some charge over it. They can be detected by mass spec. Now the charge can be anything. It can be a single positive charge, it can be a double positive charge, or it can be a negative charge, or it can be a radical ion as well. Charge can be anything. Only the primary requirement is it should be able to sustain a charge over it. Now, how do we charge a molecule? There are various factors by which we can give a charge to the molecule. The simplest thing is I can attach a proton to it. So hydrogen stripping of the electron, I can attach a proton to it, and because of the proton carries the charge. So if this is my molecule, if my molecule is M, I can attach a proton to it and it becomes positively charged. Similarly, if this is my molecule, if I remove H from it, it becomes negatively charged. During the radical cations or radical anions, if I can knock off one electron from it, then it can achieve plus and dot radical ions. So radical ions are also possible. Various ways to do it. Most commonly, you will get signals like this. So let's say, and let's go into data analysis. Little bit of data analysis I'll mention here. So let's say if your molecule weight is 100, so you will get a peak at 101. Why? Because hydrogen will contribute the one to it. So you'll get a peak at 101. Similarly, let's say if I am able to charge the molecule using the sodium ion. So let's say the molecule is 100. Let's say the molecule is 100. So sodium is 22, 23, 23. So you will get a peak at 123. Potassium 38, 38, 39, something like that. So you will get, if your peak is, if your molecular weight is M, it's 100, you add the 39 to it or 38 to it and you get it. You get that added. So this is how you need to charge the molecule. This is one important, people ask, generally freshers, they ask this question, what kind of molecules or what kind of species that you generally detect in a mass spec, and is it a universal technique or not? So this is some small pointers there. Okay. So see again, when we talk about sample going into mass spec, you realize very rarely you will get a single peak. You will get lot of components that are being ionized, lot of hundreds thousands of compounds that are ionized suddenly. So if you directly put into a detector, you'll get a jumbled up signal where all the components are giving the signal and you don't know what is coming from where. So what you have to do, you have to then separate these ions, and that is the part of the analyzer. The analyzer, that is the heart of the equipment. So the analyzer, what it does, it separates the ions based on mass to charge ratio. We'll talk about what mass to charge ratio is in the coming slides. But yes, the purpose of the analyzer is to separate the ions that are generated in the source according to the mass to charge ratio, and then the detector simply detects it. The detector is not very important, but analyzer is there. Okay, so let us talk about the source. So we know the function of the source is to ionize the molecule. And ionize the molecule, let's say this is the inlet of the HPLC that is coming into the system. Now, for one, I need to do two things here. I need to convert the liquid into the gaseous state, obviously, because I cannot inject the liquid into a mass spec and then get the data. I need to convert the liquid into the gaseous state, and then I need to give the charge to the molecule as well. So this is what generally happens. So if you see what I do, I apply electric field there, and when it starts, it generates the spray, nozzle spray. And this nozzle spray, the desolvation that we refer, desolvation, ion charging, this happens during this nozzle. And this spray then goes into the inlet of the mass spec. Okay, where inlet of the analyzer, just for understanding purposes, this spray will then go into the inlet of the analyzer where the analyzer will separate them based on mass to charge ratio. So the function of ionizer is just to so is to get rid of all the solvents, get rid of the liquid part, convert the samples into gaseous state, and then ionize the molecule. Because ionization is the main requirement for a molecule to be detected by mass spec. Okay. Now there are various ionization sources available in the market. The most commonly used source is electrospray ionization. That is we actually use in our system as well. 90% of the time we are using ESI, electrospray ionization, and this is the principle. You apply a voltage, you apply nitrogen gas, you apply a capillary voltage. Basically, other things are also there, sheet gas, ghost gas. Well, the basic thing is you keep the source at a high temperature, you apply capillary voltage, and this will assist you in removing the liquid part, removing the uncharged ions, converting the ions into gas, and then going into the mass spec. There are other principles involved in the working of ESI, but this is the basic principle. ESI, electrospray ionization, works on this principle. Just like electrospray ionization. We have something called atmospheric pressure chemical ionization. Now, in APCI, what we are using gas assistance, nitrogen or something else, argon, nitrogen, people use various gases. So we are using help of a nitrogen gas to ionize the molecule. These are the function principles of that, but we don't need to go into the detail. You just you may remember that APCI is one of the ionization method that uses the assistance of a gas that can be nitrogen, argon, or things like that to ionize the molecule. Okay, these are the common sources that we use. We use APCI, we use ESI. That again depends upon the application, what kind of molecule you want to do. Now, APCI, if you want to work, if you want to, you know, tell me I can tell you an example as well. So APCI can be used for lipids. Yeah. If you want to do lipidomics, kind of some small molecules or lipidomics, molecules that are sensitive to temperature or something like that, you can use APCI. And ESI, we are using for the normal method. So protein peptides are generally done by ESI. So your starting point of the experiment is ESI. ESI is by default. APCI is something that you can consider when ESI is not working. Trial and error method. Now there are other exotic sources also, and these are I have just highlighted here. So Maldi is something that I started. My first interaction with mass spec was with a Maldi equipment. So Maldi is nothing but matrix assisted laser desorption ionization. So here, what we are doing, you can see in this first slide, we are using a laser. What we do, we deposit a sample on a metal plate, and then we fire a laser to it. And laser causes an ablation of the molecule, converting the solid into gas, and then it is detected. Electron impact ionization, people who are working with GCMS, they will appreciate electron impact ionization. Electron impact ionization or the EI source is basically the go-to source when you are using GCMS applications. So if you have a standard GCMS in your lab, invariably it will be connected to a EI, electron impact. And electron impact ionization will generate the radicals that I was talking about. So generally you will get M plus dot kind of radicals when you are using electron impact ionization. And electron impact ionization is a default choice for your GC application. Then other things are also the fast atom bombardment. These are highly specific sources used when your requirement is certain, not routine, or you want to get some additional data. So fast atom bombardment is also kind of things, but at least I have not used it in my last, let's say, 5 to 6 years. Okay, so we have talked about sources. Now let us talk about the analyzer. So as I said, the source will create lot of ions, and we want to separate those ions before we detect it. So there are a lot of analyzers available in the market. Certain analyzers are standalone analyzers. Certain analyzers can be combined together, sandwiched together to make a hybrid analyzer. But these are common analyzers that are generally used. So TOF is something that we have it in our CAMS facility. Our TOF is time of flight analyzer. Quadrupole is very routinely, very old analyzer, is still considered as a gold standard for quantification kind of experiment. Then again, we have FTICR. FTICR, very high resolution analyzer. It has a very good ability to separate ions. The orbit trap is something that we currently use for our proteomics protein application. We'll talk about that. Then we have some old generation magnetic sector equipment. These used to be very big analyzers. I don't know where guys might have seen it or not, because they're not generally used, but in petroleum industries it is still used. So magnetic sector is a big equipment. Approximately takes the half size of the room or something like that. Very specialized equipment, and it can be a hybrid instrument. For example, the equipment that we have in our camps, it's actually a Q-TOF equipment. So we have quadrupole and TOF both combined together to form a equipment. So, and quadrupole can also be connected with an orbit wrap. So in our equipment also we have a quadrupole there, which is connected to an orbit wrap. So the hybrid instruments are there that can combine 2 or 3 analyzers together. Okay? So let us take some moment to look at the examples as well. So let us talk about the principle of time of flight analyzer. So time of flight analyzer, as we said, this is a very easy thing to understand, so I take it very often. Time of flight analyzer works on the principle of the size, mass to charge ratio. So let us assume that there are 3 molecules and all of them has charge 1. So this is a big molecule, this is a slightly moderate molecule, and this is a very small molecule. And we allow them to run in a vacuum. So this is a vacuum. This is, if you consider these 3 as an athletes, you can consider this as a race track. Okay. So keeping other thing constant, the person who is lightest or who's the most athletic will reach the end first, followed by the moderate and followed by the heavy. This is exactly the principle how TOF works. Larger molecules will reach the detector late, lighter molecules will reach the detector fast. Okay, assuming the charge equals to 1. So people just get confused at that point of time, but assume that the charge is equal to 1, and this is the principle. The heavier molecules reach the detector late, and the lighter molecules reach the detector fast, and that is how the separation works. Now, what I can do intuitively is, if I want more separation, if I want this distance between these athletes to increase, I will increase their track length. So let's say if this is 1 meter, or let's say this if this is 100 meter, I make it 200 meters. So what happens? The distance between these three athletes will increase. Quite intuitive, right? So this is exactly what the vendors do when they talk about reflector. So what in our equipment also, this is actually the schematic of the equipment that we have in the cabs. What we are doing, we are attaching something called a reflector. So reflector is attached, and where the ions get reflected from them, and this is the detector placed here. Now, slightly going into a bit detail, I can place my detector here as well. This is the detector. If I place my detector here as well, totally fine, no problem. But what the vendors are doing is they're keeping a reflector there and placing the detector here. So what is happening? If the tube length is 1 meter, because of the reflector, the tube length now becomes 2 meters. Okay, and because of that, the distance between these three guys will increase, and the distance between these three guys is actually the resolution. Okay, we'll talk about resolution. So more the distance, more is the resolution. So this is something that you can do. So if we have, I think our tube length at TAMS is I think 1.5, 1.5, 1.5 meters, 1.5 something like that. So this is the intuition behind using a reflector, because to increase the path length and hence increasing the resolution. Now talking about the quadrupole. So quadrupole is also a type of a gold standard in mass spectrometry. So if you see a very established laboratory that is doing high regulated work, so for them, till now at least, they are using quadrupole for their quantitative work. Quadrupole is again the intuition is very easy to understand. What they do is they generate a field. They generate a field between these two quadrupoles. Now we can read about this DC voltage and a RF field is generated and DC voltage is applied. But the principle of this is they generate a field in this, oscillating field in this, between these two quadrupoles. Between these quadrupoles, these are the poles. Quadru means four, so they are generating a field in this, between this field, and they make it oscillating. So there's a oscillating field between these four fields, between these four rods, and only those ions that are able to survive this oscillation will reach the detector. Those ions that are that become unstable in this oscillating field, they will collapse with the detector, and they will not reach the detector. So we can modulate the strength, or we can fine tune this field to our advantage. Let's say if I want only X ion to go to the detector, so I can modulate this field in a way that only X ions is stable in this field and reaches the detector. All other ions, Y, Z, A, B, C, all ions become unstable in this field, and they collapse with the rods, and they get neutralized. So they are not detected. So this is the basic operation of how the quadrupole works. Now, again, you can combine three quadrupoles together. Actually, this is the standard setup that is used. Three quadrupoles together, and each quadrupole can perform a different function. So when we sometime we will talk about detail about this. So again, we can triple quadrupole is again the standard for quantification, and you can use these three quadrupoles for three different purposes. So that is how you can make a hybrid equipment where all the analyzers is the quadrupole, and you can use it to the advantage. So this setup is the gold standard for quantification currently. We can talk about Orbitrap as well, but mostly people use triple quadrupole for quantification experiment. Now, let's talk about the Orbitrap. So Orbitrap is a proprietary analyzer that came into market little late in when you compare it to a triple quad at the top. It is a proprietary of Thermo Fisher. Okay, Orbitrap, Thermo Fisher has a patent protection on that. So Orbitrap is again the equipment that has gained a lot of traction. It is very popular among people who are doing small molecules or protein, because the resolution part. The resolution is very high. The scanning speed is very good, and again, it works on the same principle. We have a spindle electrode. It creates the rings of ions that correspond to a very specific M by Z, and then rings are sequentially injected into the detector, and this is of the detector. It is detected. Okay, so this is a schematic of the instrument that we actually have in our laboratory. And this is the working principle, ion suppression. Now let us talk about the application part. Now we have covered a lot of theory part. Let us talk about the application part. So the application part is, as I said, can you operate LC standalone? Yes, you can operate LC standalone. Can you operate mass spec standalone? You can definitely operate mass spec standalone. But what is the advantage? LC, what LC will do, if you are talking about a mixture of peptides, it will resolve the peptides. It will separate the peptides, which will in turn help in efficient ionization, and you get an additional dimension because chromatography will give you RT. So you have a RT for that particular peptide. Mass, what will be? It will do. It will identify the mass, and there is something called MSMS. It will fragment the mass. That's how you will confirm the identity of peptide. So you are getting two-dimensional data. You are getting RT as well to confirm the identity of the protein, small molecule peptide, and you are getting mass data to confirm the identity of the peptide. There are two data that you are using to confirm. Okay, so that is the advantage of using combining LC with MS. Now let's talk about protein. Now it's slightly complicated, but even if you have no background on proteins or so protein, we can consider it to be a big molecule. So that's slide number 2 in my presentation. This was a picture of this only. So this is a protein, it's a big molecule. So obviously I cannot inject the entire, you can inject the entire protein into the mass spec and get a signal. But the other more refined way would be to cut the protein into very small pieces and then inject it into the mass spec. So you get a lot of information, and then you combine, you sort of combine the picture, the puzzle together, and you get the structure of the protein. So the bottom up approach means you cut the protein into very fine pieces, smaller pieces. Middle down approaches, you still cut the protein, but into slightly bigger pieces. And the top down approaches, you inject the entire protein into sample. Now, each of these things have their own advantages. We can read here. What are the advantages of using top down? What is the advantage of using bottom up? Middle down also you can use. So in our laboratory, we routinely use all these three approaches to confirm the structure of the molecule. Every technique has its own pros and cons. So when you actually start working on it, you will appreciate it. What we actually do. What is the reason for doing all these three strategies? Okay. Now again, what if I use for this protein work? Now let us assume that I have done this thing. I have taken a big protein molecule. I have broken down into smaller pieces. Now I am to analyze. So what I do, if I inject only LCMS workflow, all that I will get is I will get only suppression, and I need to confirm the protein peptide by RT. I need to confirm the small pieces that we are generating only by RT. There is no other data available to me. Okay. But if I connect it to a mass spec, what I can do, after the LC has been able to separate it out, I will inject it into the mass spec and get the signal. So if I use only MS-based workflow, I will not be able to perform this partial separation. I'll get a very complicated spectra. The source that is responsible to ionize the molecule will not be able to do his job efficiently, because assume that the source is getting millions of, or let's say thousands of peptides together. So it will not be able to efficiently ionize those molecules. But if I use the if I use LC to partially separate the peptides, then it might receive 1 or 2 peptides per second or something like that, and it will be able to efficiently ionize it. So because if I efficiently ionize it, my chances of misidentification is less. Now let us talk about the basic terminology. For example, somebody comes to you and give you a spectra, and they say just evaluate the quality of the spectra. How does the quality? What is my spectra? Is the spectra good enough, or do I need to work on that? So there are certain terminologies that you should keep in mind when you talk about when you start interpreting a spectra. The first important thing is the ppm accuracy. Simply put, ppm accuracy is the difference between the actual mass and the observed. What is the theoretical mass that you calculate using pen and paper? What is the theoretical mass of the molecule that you are expecting, and what is the mass that your equipment is giving? 99% of the time, the equipment will not give you the true mass. It will be slightly off, 1 or 2 ppm, slightly off. It can be, let's say, for example, the true mass is 100. The equipment is giving me a mass of 100.002. So then I can, how do I gauge what is the error? So there is a formula: measured mass minus true mass divided by true mass into 10 to the power of 6. And I get a figure of some error. Now this is a figure that your manager or your client might look at. So if you say that, if you go to your boss and saying that I have a method developed, the ppm error is 50. So he'll first ask you what kind of equipment you are using. If you say that I'm using a Orbitrap kind of equipment, then she will not accept it, because she knows that the Orbitrap has a very high resolution, a very high mass accuracy. Then she go back, get a 5 ppm error, and then come back. Okay, but same thing if you go on a triple cord on a QTOF equipment. and you again go to her and you say, I'm working on a Qt of equipment and I'm getting an error, mass error of 20 ppm, she might accept it because that is the backdrop, or we know that resolution or the ppm accuracy might not be very high for a Qt equipment when compared to the orbit. But Qt has its own advantages that we'll discuss some other day. Okay, so ppm accuracy is one of the most important criteria. It tells you how close is your observed mass to the true mass. When you talk about very high performing equipment like an orbit wrap or something like that, 20 ppm generally I would say is a cutoff for small molecules. 5 ppm is generally accepted, but 20 ppm might be accepted in certain cases. When we talk about orbit wrap or when we talk about Qt equipment, this condition is again relaxed. Then even then I don't go beyond 20 ppm because okay, it is low, but it should not be that low because I know the resolution and the performance of the equipment. If you talk about quadrupole, yes, quadrupole is a gold standard for quantification. But ppm accuracy, I still have to be very relaxed on that. So that is the kind of equipment. So one more important parameter is ppm accuracy. The other important parameter is resolution. As I said, when you're talking about most of your industry work or most of the time, you're going to inject complicated sample into the system. Suppose I'm injecting a component that has two, I'm injecting a sample that has two component into it. So it can be resolved this way. The distance between these two is basically known as resolution. The formula to calculate it is this, but it is basically known as resolution. So you can say that at resolution 1000, these peaks are not completely resolved. At resolution 5000, these peaks are completely resolved. So resolution, this is the meaning of resolution, the separation between two critical pair of peaks. If the resolution is low, those might not be completely resolved, and there's a completely resolved resolution is this. It is completely resolved, then the resolution is high. Again, this resolution is an endpoint for your method development. So when we talk about method development some other day, uh, what is the endpoint of your method development? Till what point you should develop a method? So your manager, she will give you a list of acceptance criteria. Don't stop until you reach a resolution of X. If you're talking about HPLC, she might say that don't stop until you reach a resolution of 2. Don't stop until you reach a resolution of 5. So this is the end point of. So you should develop your method until you reach that resolution. And ICH, that ICH is a, or FDA or anything, TP or something like that. They also have a method development criteria. They say that we'll consider your method to be okay, resolvable when your resolution between a critical pair of peak is at least 2. In HPLC, it is at least 2. So resolution generally defines how well your peak are resolved. If peaks are very well resolved, the resolution will be very high. And if your peak is not resolved, then the resolution might be low. Again, what is the limit to get high resolution? Generally, minimum 2. The official requirement is 2. But your managers might say, you have achieved 2, but go to 2.5 at least. So that in future cases, if somebody else is doing, if the system changes, it doesn't drop down to 1 point, it doesn't go below the acceptance criteria. So minimum acceptance criteria is 2, but you develop up to 2.5 and keep just to make some adjustment in future. If there is some drop in the resolution, at least it will not go below the accepted norm. So this is the resolution basically. Now this is a concept of mass. Again, something that we did in our SSC or HSC level, but at this point it is very important to revise the concept of mass because it plays a very important role. And generally, again, people who are just starting into mass spec, or people who are doing quadrupole experiments, or people are doing uh, who are just starting to do mass spec, for them it is very important to understand the importance of mass calculation, molecular rate. Again, very trivial, but it is interesting. And people who are actually planning to work on mass spec, this is a very good information, what kind of equipment that you should choose. So let's say carbon. Let's start with carbon. Carbon has three isotopes, theoretically, C12, C13. Atomic weight of C12 is 12. Natural abundance is this. So this is the given information. Okay. Now let us talk about average mass of carbon. If I want to calculate the average mass of carbon, what I do a weighted average of it. So weighted average means 12 multiplied by the abundance plus 13 or 13 whatever it is, multiply its abundance, and 14 multiply its natural abundance. So I get an average mass of carbon. This is the average mass of carbon. And this is an example that I've taken. So if I use this concept to calculate a mass of this particular drug, it comes to be around 338.7673. But this is the concept of average mass. Now let us talk about the nominal mass. So nominal mass is average mass, the whole part of the average mass. So you just remove that points after decimal, and then you get the nominal mass of the molecule. So if I calculate the nominal mass of the same molecule, I will get 338 because obviously I'm ignoring the decimal component. This is the basic definition. There are some other things also you need to consider, but this is the basic definition for nominal mass. Now, in our case, we are more interested in the monoisotopic mass because we have a very powerful system. In monoisotopic mass, you have to take the atomic mass of the most abundant isotope for calculation. For example, carbon will not be a good example. Let us take hydrogen. Hydrogen, okay. Hydrogen. The more if you talk about the hydrogens, this isotope, 1H isotope has a mass of is the most abundant isotope, and it has a mass of 1.007825. To remove proton from it, the electron mass should be subtracted. But ideally, it has a mass of this. And for your calculation of monoisotopic mass, you should take this mass for calculation. Similarly, for and again, one good interesting case I will show you that will make it a bit complicated, but nonetheless, I'll try to explain. Let us take chlorine, for example. So most of us who have taken basic course in chemistry, you know that chlorine has two isotopes that are 70 distributed approximately in the ratio of 75 to 25. For example, if my molecule has chlorine, it's let's say if I have 100 molecules of that contains one chlorine atom into it. So 75% of those molecules, that is 75 molecules, will have chlorine 35 in it, and 25% of the molecule will have chlorine 37 into it. Okay. So, and again, if we go strictly by the definition of monoisotopic mass, we should take the mass of the most abundant isotope, that is this. So I will take this. Okay. Now, interesting cases, if you understand this, this is good. Interesting cases, you see the abundance part here. In chlorine, the abundance is pretty high for the other isotope, 25%. Here it is only 1% and 2%. So in chlorine, the abundance is very high. So if I say, if I have 100 molecules of chlorine, if I have 100 molecules that contain one chlorine atom, so 75 of those molecules will have C35 and 25% of those molecules will have C37 into it. So in the mass spec, you will get two signals corresponding to the same molecule. So let us say if I calculate the monoisotopic mass using the Cl35 chlorine 35 atom, I'll get 338 and something decimals. And if I use the monoisotopic mass of chlorine 37, I get a mass of 340. So if you are working and if you inject the same sample, pure sample into your mass spec, you will get two peaks. Why? Because the natural abundance is very high. So you will get two peaks that are separated by the Dalton difference of two Daltons, obviously because the Dalton difference is 2, and their intensity would be in the ratio of this 3 is to 1. We generally call it 3 is to 1. So the intensity of the compound that has Cl35 attached to it, if we consider it to be 100%, then the compound that has Cl37 attached to it, that will have a abundance of 3. So 100 is to 3. 100 is to 30. So that is a diagnostic signal. To compare your identity of the molecule. For example, your synthesis team is working on certain drug and they say that we have incorporated chlorine into it. Let's say, just tell me whether the chlorine has been incorporated or not. So what you do, you inject the molecule into the system and see if you are getting two set of peaks separated by a two Dalton difference, and the intensity is in the ratio of 10 is to 3. 9 is to 3, 10 is to 3, whatever you call. And if you do get this, then you can say yes, one chlorine atom is there. Similarly, for bromine, you guys might know bromine has a 50-50 abundance. So 79 bromine is 50% and 81 bromine is again 50%. So if the same guys come to you and say, now we have incorporated bromine, inhalers, and that they have bromine into it. So you can say, they will say that check whether bromine is incorporated or not. So again, you inject into the system and you see whether you are getting two sets of peaks, two peaks. If the two peaks are separated by a 2 Dalton difference and their intensity is approximately equal, then you might say, okay, so one bromine is incorporated into it. So this is something diagnostic that we use for halogens to confirm the identity of halogens as well. Now, towards the last part, it's the interesting part. Now we are going to talk about proteins. So simple, this kind of data is easy to understand. Okay, you can easily deduce. Let's talk about proteins. I've taken this peptide as an example. So guys who don't have protein background, don't worry. This is just a peptide with a single letter code of amino acid. Now, if I apply the concept of average mass and calculate the average mass of this peptide, it comes to be around this 2136.03. But if I use the concept of monoisotopic mass and calculate the difference, it comes to be around 2134. So the same molecule, and you can appreciate the difference. If you use average mass, 2136. If you use monoisotopic mass, 2134. So what is it actually? The difference is almost of $2. And when you are working with a very complex data set, you need to be very precise what mass you are actually expecting. So for an Orbitrap equipment, I am expecting the monoisotopic mass. I should get the monoisotopic mass. So you can appreciate the importance of mass and the type of mass spec that you should use. That depends upon your knowledge of this monoisotopic mass and what should show up. So this is whatever we talked in the last two slides. This is the importance of this slide. This slide demonstrates the importance of that concept. Okay. Now, couple of slides remaining. Just bear with me. So let's talk about monoisotopic mass and how actually you get the spectrum. We are now going to talk about. I'm going to show about some data that we generally detect. So first, most important thing is I told you we need to charge the molecule. Neutral molecules will not be detected by mass spec. So because neutral molecules are not detected by mass spec, we are detecting not the mass but the mass to charge ratio. You see M by Z, M by Z. Here also M by Z. A mass spec raw in the raw form does not detect the mass of the molecule. It detects the mass to charge ratio of the molecule or the entity that we are talking about. In most cases, charge equals to 1. So m by z, that is equal to m divided by z, where z equal to 1. So m is nothing but the molecule. I have explained that in this detail. Let us say I have a monoisotopic mass of a molecule at 834. Now, if I want to ionize the molecule in the ionization source, the proton gets attached to it. So the mass becomes 834 plus the mass of the proton. And you get this P mass of this entity comes to be around this. Now, because only one proton is attached to it, there is only one charge. So Z is equals to 1. So M by Z is nothing but this divided by 1. This is something 835. Then we are getting the same. So this is the data that we have generated in our laboratory. Many of the data that we generate. And here you can see. Here the software is automatically annotating the charge state of the molecule. That Z is known as the charge state. So it is saying that this peak that we have identified, it has a charge state of 1 and it has a mass of this. Now let us go into our example. Let us make things more complicated. Now what we are doing, again, let's take this peptide for an example. It has a mass of 2134, something like that. But to this peptide, two protons are getting attached. Okay. So there are two charged. There are two, the Z equals to 2 here. Okay. So what I will do to this, I will add the mass of two protons. M plus 2 into this. I get this particular value. And but my Z is 2 here. Z is 2 here. So my M by Z becomes this mass divided by 2. I'll get this peak. So ideally, I will get this peak. This is the peak I should get in my raw spectrum. And this is what I'm getting in the raw spectrum. And the software is, the instrument is saying that, okay, this is the peak and this is the charge state of the molecule. Now there is something called deconvolution. What I want to do, I will convert this deconvolution and I will get the actual mass. So the actual mass comes to be around this. Okay, and here you see, here the scale was m by z. Here the scale becomes mass because I'm stripping the charge state 0. I'm making a difficult topic, but this is the essence of it. And the best part is all of this is done automated. Everything is done automated. You don't need to worry about it. Everything is done automated. So there, here we have seen how mass spec takes an advantage. So it gives basically it gives a lot of information. Lot of information. Your appetite for information should be very high when you're talking about complex mass spectrometry experiment, because this is just a single spectrum. In my experiments that I do, I get around somewhere around 10,000 to somewhere around 20 to 50,000 spectra that I get, obviously. So manual interpretation is humanly not possible. Only what I can do is I can take an appropriate software, feed it particular parameters, and then allow it to run. See how it analyzes. Then again tweak the parameter and then try to run. So this is how we do it. And this is the last but one slide of the presentation. Now we have talked about small molecules. We have talked about molecules that have mass very small, 1068 or something like that. Let's talk about a protein. If you remember my second slide, I gave you a structure of a protein that has a mass of approximately 145 kilodaltons. Now my mass range is old. This is again an interview question. So my mass range for the current Orbitrap equipment is around 8,000. And that too, we have taken an advanced version of the benchtop model where the instrument is generally has the capacity to scan masses m by z up to 8,000. Generally, it will scan only up to 6,000, but we have taken something that is called a Biopharma upgrade. In Biopharma upgrade, you can scan up to 8,000. So somebody might ask you, we are operating an equipment that has the highest capacity of 6,000 MIV. It cannot scan anything beyond 6,000 capacity. Then how are you detecting a molecule that has a mass of in kds, that to 145 kd? So here you can come to the concept of charge state again. You see, my mass was 2136. I divided by the number of protons attached to it, and the mass directly became half. From 2136, it became half. So in this case, assume this is the mass 148200. If this is the mass and there are 45 protons attached to it, then it will get reduced by 40 times. And then it will fall into my scanning range, and then you will get this kind of stuff. Okay. So these are the charge state envelope. We don't worry about it. This is charge state envelope. Here the charge is different. Here the charge is different. This peak has a different charge because it will not be because protein or antibody has number of places where a proton can get attached. So proton can occupy 45 sites, it can occupy 30 sites, it can occupy 12 sites, it can occupy 80 sites as well. So this is the envelope that you get, where the number of protons that are getting attached to the antibody is changing. But again, after deconvolation, that the process is automated, you will get the mass that is corresponding to this. So I am getting 148,200 is the expected mass. I am getting a mass of 148 and 148,199. Only the difference of 1 Dalton. So that is how we develop a method. It is not easy. I'll be mistaken if I tell you it is easy. But once you start doing practically, you will appreciate. You'll understand how to develop a method and go about it. So this is the basic of mass spectrometry. We talked about little bit about the basics. We look at the instrumentation as well, and ultimately we look at certain applications. So I hope I was able to convey whatever I wanted to convey, and you got a little bit interested into mass spec, and uh, that's about it. Oh, one last slide is there. Sorry. So yeah, now let's talk about a small slide just to give you something to read in case you are more interested. Now, how do I confirm the identity of a particular molecule? Let's say 835. Now, there is a universe of molecules that will have the same mass, 835, or for that matter, 2135 also, or 835. So, how do I confirm among, let's say, just for argument purposes, there are, let's say, 10,000 molecules that have the same mass. If you just go into Chem Spider and type this mass, you'll get a list of molecules that have the same mass. So how do you know that, okay, my molecule is this and not this? It is X and not Y or Z or A or B. So one way to confirm the identity of the molecule that has same masses is to use the concept of fragmentation. So what I will do, I will tell the equipment to take this 835 peak that you are getting and you fragment it into smaller pieces. Now fragmentation, we can consider it as a fingerprint. Just as you can identify a human, mostly certain cases, by a fingerprint, you can confirm the identity of a molecule by the way it breaks. The system will do nothing. It will take the molecule, it will subject it to high energy, and it will break it into smaller components. And this smaller components is considered as a fingerprint for that identity of the molecule. Now the good part is, the instrument will fragment it into smaller parts, and we exactly know how the equipment will fragment it. We will exactly know what kind of ions will be generated. I can take a pen and paper and I can show you why is 707 generating after I bombard this molecule. Why is 400 getting generated? I actually know the rules of how this molecule, how this small masses are getting generated. So I'll do the same thing. I'll tell the equipment, do one thing, so you fragment the molecule with very high energy. At the same time, you generate a theoretical spectra as well. You generate the theoretical spectra. These are the rules. The software knows, very intelligent. They know it will generate the theoretical spectra and it will match the theoretical spectra with the observed spectra. This is the matching. So the red thing you see, it is the match, that it is the theoretical spectra and the matching spectra. Black one is the actual spectra, and the red thing is the theoretical spectra that is generated by the equipment and it has been matched with the ions. So it will see. So generally, I can say, okay, theoretically the peptide is supposed to generate 50 fragments, and the theoretically 50 fragments are generated. Even from those 50 fragments, if you are able to, let's say 70%, 35, if you are able to match at least 35% of the fragment from the experimentally generated spectra, give me a good hit. So it will do the calculation, it will see if it is matching, and it will give me a score. Okay, your theoretical spectra matches with the observed spectra up to 80%, up to 90%, and that can be a cutoff. If I'm very stringent, I will say 90% cutoff. If I'm slightly stringent, I can say 70% cutoff. So this is a strategy to confirm the identity of the molecule at two stages, at MS level also and at MSMS level also. And the last thing, now how do you do the MSMS? There are two strategies, again, slightly complicated, but when you start doing proteomics, this is very useful. So how do I select the fragment? This also is completely automated. I will tell to the equipment, select the top 10 peaks for fragmenting only. This is called top 10 feature, data dependent acquisition. So I'll get a spectra and I'll tell the equipment, select only the top peaks, top 5 peaks. So here it is selecting top 5 peaks based on the intensity and fragment them. So this is known as DDMS approach, data dependent acquisition. In data independent acquisition, I am giving sequential windows. You see, these are the windows. And I'm saying to the equipment, fragment all things that come in this window, then fragment all things that come in window, then fragment all things that come in window, and then generate this effect. So these are the two approaches that are basically used, typical approaches, when you do proteomics, when you have large 5,000 to 10,000 proteins in a sample and you want to confirm the identity of the protein. So there are two approaches. You can read further. It's very interesting. It is called DDA, data dependent acquisition, and the other acquisition, the typo error here, it should be DIA, data independent acquisition. So thank you. Yeah, that's it. Hope you guys understood, or I was able to convey what I was decided. Okay, over from me, actually.
Yeah. Thank you very much, Ijaz. I think you not only touched upon the basics of HRMS, but you also did a very detailed presentation on LCMS. I think definitely participants have gained a lot from the session. What I'll do is I'll quickly open the floor for any queries that anyone may have. So if anybody has any queries, can quickly type in the chat box, and alternately you can also go ahead and unmute yourselves and ask the queries. You can. So Ijaz is a specialist in mass spec, and he's worked extensively on not only the high end machines, but he has done a lot of quantitative and labeling works also. So if you all have any specific queries related to your particular analysis or something, please go ahead and share your queries here, and we'll be happy to answer them. Yeah, any specific queries, any you all can also raise your hand so we can unmute and take them up. Okay, so I think maybe I think there is. Yeah, so Shiv Prasad is asking, are you giving any practical training on above protein analysis at your site? So yes, Shiv Prasad, we do provide hands-on training sessions on such techniques. In fact, couple of months back we did one on intact mass analysis, and we will be a couple of them on peptide mapping and other. This is also planned in the upcoming months. So please stay tuned. You can visit our website to get information about the upcoming events, and you'll also be added to our mailing database where we regularly give updates of the upcoming workshops, so you can sign up and you can attend them. There's another question. What is the difference in UV detector used in HPLC and UV? Uh, this question is from Aditya. Ijaz, do you want to take this up? What is the difference in UV detector used in HPLC and UV?
Yeah, 1 minute. Let me see the question. Just 1 minute. What is the difference in the
Sure.
UV detector used in HPLC? Yeah. Okay, nice question. Nice question. Exactly. So the Aditya, is it? 1 minute.
Yes, Aditya.
Aditya. Huh. So Aditya, very nice question. So again, the answer to this may be very intuitive. In HPLC UV detector or in a UV standalone UV spectrophotometer, the principle of operation is very same, exactly same. But in HPLC, in a UV detector that is connected to the HPLC, you are analyzing a continuous flow of a sample. If you have used the HPLC standalone detector, what you do, you fill a vial with your sample, you fill a cuvette with your sample and put it into the detector and then it analyzes. But in HPLC, what you have to do, you have to analyze a continuous flow of the sample that is going. So the engineering part or the part is to be modified in such a way that it is able to analyze only, it is able to successfully analyze a flow of the sample. That's it. Otherwise, the bulb, the UV lamp is same, the detector is same, the grid is, the prism and everything, grid is everything is same. Next question.
I hope, Aditya, that has clarified your query. Okay, yeah, he says thank you. So, in case you all have any other queries, you all can always reach out to us. Our email IDs are there, and all our details and service offerings are listed on the website. As we come to the end of the session, I'll take this opportunity again to thank Ijaz, for preparing such an elaborate presentation and for sharing all his insights and inputs with us. And thanks, Ijaz, once again. And hopefully, all our candidates have benefited from this. And yeah, I think thank you once again, and thanks to all participants for also joining. We'll be happy to support any of your mass spec queries in the future. So thank you, and with that, I will now end the session. Please do provide the feedback. It's very important. I have shared the link in the chat box. You can share what you liked about this workshop, and you can also suggest topics on which we can conduct, future talks. So please do share your feedback. It's very important for us. Yeah. Thank you, everyone. Thank you so much.
Okay. Thank you,
Also,
guys. Thank you.
this session has been recorded, and we will be uploading it on the YouTube channel, and I will share it over email with all of you. Yeah. Uh, I think there's one more question, Ijaz. If you just have last 2 minutes, can you
Sure,
make a
sure.
presentation on Empower 3 software use? Oh, okay. I don't know.
Yeah.
Let's
So
see.
let
We
me
will.
just. Yeah, yeah.
Sure, Ijaz. Go ahead. Yeah.
Yeah, sure. Yeah. Can you make a presentation on Power 3 software? Yeah, yeah. So, yeah, Aditya asking interview related questions, I guess. So, yeah, Empower 3 is actually, as you rightly pointed out, it's a standard software that is used in, I've used it. I've used it in a lot of other companies that I was involved in. And Empower 3 is a straightforward, only thing is you need a couple of pointers that you need to remember when you're using Empower 3 is it will not let you do manipulation. You don't need to worry about manipulation because this Empire 3 software is compliant software. So even if you want to pick a peak that is not actually a peak, the Empire 3 will say it is not a peak and it will not generate a peak. That is something that you need to be very aware of. You should. It is very well compliant software, so you don't need to worry about compliance. Okay. Empower 3 software, and again, it is generally in our lab we are not using Empower 3 software because it is an entire enterprise level software. Whatever system that we are currently using are standalone systems. I mean they come with their own software suite. But again, once this is something that we have in our mind, ultimately when we decide to go expand, and this is something that we want to Empower 3 software that we'll install there. There is other called Chromeleon. So Chromeleon and Empower 3 are two market leaders that are currently being utilized in a lot of the companies, and they are FDA software. But I'll be happy to share you with some resources, Empower 3 software resources that I can share. And one interesting point, again, to make it a little complicated is, now proteins and proteins workflow as was now when I started working on Empower 3, it did not have any space for proteins because protein was slightly different. So now, but the newer versions, they are incorporating protein workflows into it. Chromelon is also incorporating this new workflows and new things like statistic based method development, design scope, and these things are incorporating. So it's very pertinent for guys who are actually planning into venture into pharmaceutical analysis, regulated pharmaceutical analysis. They should uh, read about it at least at basic level. So I'll share some resources with the team, and maybe they'll put it somewhere, and you can get. Yeah.
Sure, I think that would be good. And maybe once we receive it, we'll definitely share it with you.
Yeah.
So, yeah, thank you, everyone. And with that, we'll now end the session and look forward to meeting you all in the next session. Thank you, everyone. Have a great evening ahead. Yeah. Bye.